Good morning. My name is Sue Kowalski, and our presentation today is about the data for policy research, accessing and leveraging NWEA's map growth science data. And I want to start by introducing myself and my colleagues. My name is Sue Kowalski. I am a lead research scientist in the Research Policy and Partnership team at NWEA. And my emphasis is on analyzing NWEA data specifically related to science education policy questions and trying to make those findings accessible to practitioners. And my colleagues joining me today are Susan Berg and Scott Peters. Susan, do you want to introduce yourself?
Sure. So I'm Susan. I taught mostly high school science before coming to NWEA, and so here I'm on the team that develops the science map growth assessments.
And Scott?
Hi, everybody. I'm Scott Peters. I have no content area expertise about science whatsoever. I'm the Director of Research Consulting at NWEA, so I work with Sue on a lot of our external research collaborations that hopefully will include science data.
Thanks. Okay, so a little bit about NWEA. This slide shares a little bit about our organization, and I won't read it to you. But what I will say is that we at NWEA believe strongly that assessments and the data they generate should be used to improve instruction. So if schools and districts administer assessments and do nothing with the data, that's really a missed opportunity. Our research policy and partnership team really leans into this belief. So we are analyzing data to inform educational policy nationwide with particular emphasis on analyses benefiting practitioners. But there is so much data and there are so many research questions, we certainly cannot pursue them all. And we hope today's session will inspire you to think about how NWEA's map growth data might be useful to you as you pursue your own research questions. So let's imagine this. We've got a science education research journey. You're a science education researcher with a pressing question. How do differences in state science standards impact student learning outcomes across the country? It's a question with real policy implications, one that could inform decisions about standard alignment, equity, and instructional support. But to answer it, you need science assessment data that is aligned across states, is reliable, is valid for your purposes, and it's available at scale. So here's what that journey really looks like. Step one, develop an assessment. You need an instrument that aligns with your research goals and reflects current science standards. That means hiring experts, designing items, piloting versions, and refining them. That's high cost and it takes a long time. Step two, you must test the assessment with a sample population to evaluate its reliability and to ensure its validity for your purposes. This involves recruiting schools, securing permissions, and analyzing psychometric properties. Cost goes up and time gets even longer. Step three, now you need a large, diverse sample to draw meaningful conclusions. This means coordinating logistics, training proctors, managing data collection, and cost and time just keep going up. And after all that, you still need to clean, analyze, and interpret the data, hoping it's robust enough to support your research claims. So now let's take a moment and remember the current funding climate. We've all seen the news, and none of it is good. None of it is good news for education researchers. We've seen cuts to NSF, cuts to IES, and fierce competition for a limited amount of foundation funding. We are facing the biggest disruption to education research funding that I have seen in my entire career. So putting it all together, the cost of developing assessments is high. The cost of validating and administering assessments is high. And there is a budget hole where research funding used to be. So in this presentation, we will be sharing with you information about NWEA's map growth science assessments. Depending on your questions, you may be able to leverage NWEA's data to pursue your research rather than starting from scratch. And if the stars align, map growth science data may open doors for you to conduct the kind of policy research you want to conduct that may open doors for you to conduct the kind of research you want to conduct that might otherwise be out of reach. So let's start with a little overview of map growth in general. And this information applies to all map growth assessments, really regardless of subject. Map growth is an interim assessment, which means it is designed to be given periodically throughout the school year to monitor student learning and growth. Districts typically administer it up to 3 times per year in fall, winter, and spring. The fall assessment provides a baseline. A winter administration would allow schools to check mid-year progress and adjust instruction. And spring offers an end-of-year measure of growth. And because the test is adaptive, each administration provides timely, actionable data about where students are in their learning and how instruction can be targeted to support continued progress. Also, map growth science, like all map tests, is computer adaptive. So we start by administering an item of medium difficulty to a student, and if they get that right, we give them a harder item. If they get that wrong, they get an easier item, and so on, until we obtain a good estimate of the student's ability in that domain. Map growth is norm referenced. It's a norm referenced interim assessment. And we recently completed a full update of the national norms across all subjects and grades. So a test that is norm referenced means it includes information about a comparison group or information on the interpretation of those scores relative to the reference population. And a simple analogy helps illustrate this point. Caitlin Clark is 6 feet tall. Her height doesn't change, but if we compare her to other NWEA players, she's right at the 50th percentile. On the other hand, if we compare her to all US adult women, she's at roughly the 99th percentile. The metric is the same, her height, but the reference group changes the percentile. So that same principle applies with map growth norms. Our new reference group is the current national performance, and because national averages have declined since the pandemic, a given score may map to a different percentile rank than it did under previous norms. Map growth tests are, as the name indicates, designed to measure growth. They are developed using the Roche measurement model to have a vertical scale with items and people measured along the same logit scale. And because we have this vertical scale, it's based on the Roche measurement model, our achievement scores fall on what is called a Roche unit scale, or in NWEA parlance, a RIT scale. And there are some important properties of the RIT scale. I'll mention them and then go into a little more detail. So first of all, RIT scores are equal interval. RIT scores are on a vertical scale, and RIT scores are stable over time. So let's unpack this a little bit. The RIT scale is an equal interval scale, which means that no matter where you are on the scale, the difference between 2 units is the same. To illustrate this with a height example, a 1-inch difference is consistent whether kids are very short or very tall. 1 inch is always 1 inch. Similarly, on the RIT scale, the difference between a 200 and 210 is the same as the difference between a 260 and a 270. So why do we care about scale being equal interval? We want to be able to use the same scale to quantify achievement across the entire spectrum of student abilities. And this requires confidence that differences between scores are consistent regardless of where they fall in the distribution. And this consistency ensures that we can accurately measure and compare student growth and achievement over time. To further illustrate this point, let's consider a case where the scale is not equal interval. Percentiles are a prime example of non-equal interval scale. This table shows household income percentiles and their associated annual income levels. A 5 percentile point difference has a very different meaning depending on whether we're at the low or high end of the distribution. For instance, a 5 percentile point increase in household income near the lower end of the scale might mean an increase of a few $1,000s, while the same 5 percentile point increase near the upper end could mean tens of thousands of dollars. So if a politician proposed a tax break equivalent to a 5 percentile point increase in your household annual income, it would have a vastly different implication depending on where you fall on the income distribution. This variability makes percentiles less useful for certain types of precise measurement and comparison. And in contrast, an equal interval scale like the RIT scale ensures that a unit increase means the same thing across the entire range. The next key property to keep in mind is that the RIT scale is a vertical scale. This simply means that we use the same scale to measure students regardless of their grade or ability level. If we look at the typical makeup of a fifth grade class, for example, you'll see a really wide range of abilities. Some estimates suggest only about a quarter of students are actually at grade level. Some are below grade level, and some are well below. Still others are above grade level. We want MAP growth to meet students where they're at. We want the floor to be very low and the ceiling to be very high so we can capture this range of academic achievement levels. The vertical scale also makes it possible to measure growth over time. With non-vertical scales, growth determinations are much more challenging. For instance, if we compared a student's grade, end of course grades, what could we conclude about her growth in algebra skills over time? Does going from an A in 7th grade to a C in 9th grade indicate that she's losing algebra skills? The RIT scale provides a continuous, stable measure that allows us to track student academic progress accurately over time, offering a clear picture of their growth. But without a consistent vertical scale, it's difficult to make accurate assessment of progress. Grades are often influenced by factors such as differing grading standards and course difficulty levels, which really obscure true growth. Finally, the RIT scale is stable over time. This means that the interpretation of the scale remains consistent over the years. So for instance, a RIT score of 220 has the same meaning today as it did 5 years ago. And this stability doesn't happen by accident. We continuously monitor the scale to ensure its stability and make adjustments as necessary. To illustrate why this is important, let's consider a case where an underlying scale is not stable over time. You might be familiar with the concept of vanity sizing. At some point, clothing manufacturers realized that our society's beauty standards and emphasis on thinness mean that people feel better when they buy a smaller size. And when people feel better, they tend to spend more money. Clothing manufacturers have taken advantage of this by changing the correspondence between underlying body measurements and numeric sizing. So for example, a 26-inch waist back in 1970 would fit a size 12, but in current sizing, a 26-inch waist is a size 0. This clearly demonstrates a scale that is not stable over time. Sizing now cannot be compared with sizing 10 years ago, which becomes painfully obvious to anyone who tries to buy a pair of vintage jeans and is shocked to realize they need to go up several sizes. In contrast, the stability of the RIT scale over time ensures that a score of 220 means the same thing today as it did 5 years ago. And this consistency allows us to track and compare student progress accurately over time, providing reliable data for educational decision-making and student support. So I've shared with you 3 important properties of MAP growth: equal interval, vertical scale, and stable over time. But it's important to also note some things that MAP growth is not. MAP growth is not a criterion reference test. It is developed using standards, but it does not claim to measure mastery of standards. How is this done? Each test is aligned to standards through item pools. We have a pool of items aligned to the specific standard in question. The specific item the student receives, however, depends on a combination of the difficulty of the item they just answered, whether they got the item right or wrong, which items they've seen in a previous administration, and the need to align a test administration with a blueprint. So for example, not all items on a science test will be related to life science. There will be some on earth science and physical science as well. We do have third-party alignment studies that verify the strength of the alignments of item pools with standards, but ultimately, because of this computer adaptive feature of MAP growth, we can't specify exactly which items students receive. So MAP growth is not criterion referenced, but this is to be expected really for any test that is norm referenced and excels at measuring growth. Last, although our main body of focus today is on science assessments, I want to make you aware of the various subjects available. We actually have a suite of assessments across multiple content areas. We have assessments in math, we have assessments in language usage, reading, and my personal favorite, science. So we talked about the RIT scale in previous studies, and it's important to note that each subject has its own scale. So a 200 in math is not equivalent to a 200 in reading. But within each subject, the map growth RIT scores are equal interval, vertically aligned, and stable over time. That was a lot of information. So before I dive into the details of map growth science specifically, let's pause there and see if there are any questions related to map growth assessments in general. And I'll stop sharing for a minute, at least so I can see everybody. So do we have any questions related to the map growth assessments in general? I'm not seeing any questions. Susan or Scott, do you see anything on there? Okay. I'll go ahead and keep going then. Okay, so let's dive in now to the details around map growth science specifically. There are really two different varieties of map growth science assessments. One is a general science assessment offered to schools, in grades 2 through 12, and it addresses standards in life, physical, and earth space science. The other is an end-of-course life science test administered to students whenever they take a high school level life science course, typically in grades 9 through 12. Now, this might be getting into the weeds a bit, but I think it's important to note that map growth science is not a single assessment, but rather a family of assessments. So on the left, the tree labeled NGSS version represents the family of assessments developed for states that have adopted NGSS-aligned standards. And on the right, the state-specific versions tree represents assessments built around individual state standards, such as Texas Tech's or Ohio standards. Each tree appears to grow independently because each assessment is tailored to its context, but they all share a common vertical RIT scale. So you might be wondering how we accomplish this feat. The answer lies in the framework for K-12 science education. This is the document that preceded the next generation science standards themselves, and the framework was tremendously influential, far more so than the standards themselves. This map was created by our colleagues at NSTA, and it shows which states have formally adopted the NGSS, that's in purple, and more importantly, which states have standards based on the framework. And then there's Florida that adopted neither the standard nor the framework. So really, with the exception of Florida, every state has standards grounded firmly in the K-12 framework for science education, whether they've adopted the NGSS standards or not. So that is what we have used to ground our science assessments. Using standards that are all grounded in the same framework, we have created assessments that have overlapping item pools and all use the same vertical RIT scale. Science scores in Texas then are on the same scale as scores in California or scores in Ohio. The next generation science standards aligned map growth item pools are designed to represent the multidimensional vision of the framework most directly. Items anchor to phenomena or problems that require students to use multiple dimensions, such as practices, concepts, and ideas together. The state-specific tests, such as those for Texas or Ohio, include item pools that are mapped to each state's standards. These standards were developed independently of NGSS, but share much of its DNA. They emphasize very similar big ideas and many of the same practices, but the performance expectations are structured a little bit differently. What's important is that both types of tests draw from the same conceptual model of what it means to do science and to demonstrate scientific understanding. That makes comparisons across test events meaningful, even though the standard alignment differs. So let's pause again. That section was brief, but I want to make sure to give you time to ask questions about the design of the NWEA science assessments before I go into the data that are available. So what questions do we have about the design of the NWEA science standards? Sorry, the NWEA science assessments.
I'll throw something out, Sue, which has come up in the context of like math and reading before, but I've never dealt with it in science, because I could imagine a science ed researcher out there wanting to study something and have just listened to you talk about the different standards and kind of domains that are covered by the science assessment. So can you or Susan talk a little bit about, the balance of those domains in the science and kind of assessments and how that might work for me if I'm a policy researcher, like what implications that has and how it kind of plays out?
Yeah, Susan, do you want to speak to that?
Yeah, I can speak to just how the different domains are represented. So the tests will have three, what we call instructional areas: life science, earth and space science, and physical science. And there'll be roughly 1/3 of the test will be each of those domains. And so we aim for about 13 items in each of those domains to get a subscore in that domain. And so there are subscores for each of those domains, and then there's the overall RIT score. As far as how that goes into policy research, maybe I'll leave for the researchers to answer, but.
And that's different for the life science end of course test in high school. That one is just life science, correct?
It is just life science. It's also divided into, actually, I forget if it's 3 or 2 instructional areas. So we'll have either 2 or 3 subscores within the more specific sub areas of life science.
Okay. Any other questions about the design of the NWEA assessments, science assessments? Let's see. Okay. Back to it. So now let's really get into the nitty-gritty details of what data are actually available from our NWEA science assessments. The basic data available from NWEA science assessments provide a really rich picture of student achievement and growth over time, as well as important contextual information about students and schools. And data really fall into 4 categories, and I'll go through each one in turn. First, we have RIT scores, which represent student performance on the NWEA macro science assessment. So these are those vertically scaled scores I described earlier, meaning they can be compared across grades to track student progress over time. RIT scores give us a precise estimate of a student's current level of science understanding, and these are collected up to 3 times per year and include timestamps to allow for the calculation of instructional weeks between assessments. And that's really important when you're trying to measure growth. It's important to know how much time students had between assessment instances so that you know how much growth to expect between those instances. Second, we can look at growth scores. So NWEA actually provides several ways to summarize growth, not just by subtracting the difference between test administrations, but by looking at something called conditional growth indices and conditional growth percentiles. So those are metrics that compare a student's growth to that of similar students nationwide, taking into account their prior achievement and their grade level. And they help us really understand whether students are growing faster or slower than expected. Third, we have demographic information. So within the MAP growth data, student grade, race, ethnicity, and gender are all directly available. And these allow us to examine differences in achievement or growth across student groups. To add context at the school level, we can merge in information from the Common Core of Data, or CCD. For example, the proportion of students eligible for free or reduced price lunch is a measure that helps approximate school level socioeconomic context. So that's not directly included in MAP data, but leveraging CCD allows us to pull it in. Leveraging the CCD can also provide the urbanicity designation of the school, whether school is public or charter, and all sorts of additional contextual pieces of information. So these designations are often very important in policy research and can be linked to NWEA map growth data. Finally, we also have course name data, and these data can provide insight into what types of science courses students are enrolled in. These are actually one of the more challenging data sets to work with. I've X'd out teacher names here, but course titles can really vary widely across districts. So we've developed and refined search strings to classify courses. So for example, distinguishing general science from physical science, earth space science, and life science. It's an imperfect process, but with careful coding, we've been able to extract useful patterns from these data. Okay, so before we go into how data might be used, what questions do you have about the data that are available? I'm not seeing any questions. Scott, did I miss anything? Okay. So NWEA data offer really valuable opportunities to study the effects of education policies and patterns in science learning over time. And because the assessments use this stable, vertically scaled measure, we can examine student achievement and growth across years and grade levels in a consistent way. So one of the first ways that NWEA data can be used is that they are really well suited to studying the influence of state or district policy changes. So for example, if a state implements a new accountability system, say it changes graduation or testing requirements, or it adopts new instructional time mandates, we can use NWEA data to see how student achievement and growth trends respond at the district, school, or subgroup level. NWEA data can be used to examine trends in science achievement and growth over time. So we can track long-term patterns in science performance, including whether growth accelerated, slowed, or stabilized following major statewide or national events, such as the COVID-19 pandemic. We can also look at science in relation to other subjects. So for example, whether science growth is keeping pace with ELA and mathematics over the same period. Finally, these data can illuminate differences across schools and instructional contexts. For example, we might compare trends in science achievements for schools that organize science instruction differently, such as those that use dedicated science blocks, like they offer science in a certain amount of period every day, or they actually integrate science instruction across subjects. We could compare science growth and achievement across those different contexts. So overall, NWEA data allow us to connect policy changes and system-level patterns to student learning trajectories in a way that few other data sources can. So as described earlier, MAP uses the RIT scale, which is that vertical continuous scale. So it can be compared across seasons and years. And this allows districts to see how much students have grown, even if they've started far above or below grade level. But because of this design, MAP growth is not aligned to a single year standards in a way that supports percent proficient or mastery cut scores. Instead, it provides actionable information about where students are on the learning continuum and how fast they're moving. That said, we do have linking studies that carefully examine map growth RIT scores relative to individual state assessments. And these linking studies provide predictive information to determine if a student is on track for proficiency, but it must be linked to that criterion reference test, information that is not inherent in MAP itself. So for MAP mastery or standards-based judgments, educators need assessments built for that purpose. MAP growth contributes by showing progress, identifying instructional readiness, and highlighting whether students are accelerating, maintaining, or slowing in their learning trajectories. And this is one last piece of information about what these data cannot be used for. NWEA has specific restrictions on how the data can be used by outside researchers, especially since NWEA is now a part of HMH, or Houghton Mifflin Harcourt. So one important limitation that you should know is that NWEA will not provide data for studies that directly analyze, evaluate, or compare instructional programs, assessments, or products that are seen as competitors to HMH's portfolio. And this restriction really applies even when the data are de-identified. The issue is not privacy, but competitive impact. The goal is to ensure that data access does not inadvertently support research that could disadvantage HMH in the marketplace or conflict with customer contracts. So researchers can still pursue work focused on policy, measurement, growth modeling, equity, or general education questions, just not product efficacy or comparison studies involving competing vendors. That said, this limitation applies only to data requests directly from and to NWEA. So if you collaborate with districts who use MAP growth, districts are free to share and use their own data for whatever purpose they wish. So let's pause there. What questions do you have related to how NWEA data may or may not be used? Scott, do you want to say anything about the linking study aspect? I went through that pretty fast.
Yeah, this is something that's probably kind of unique for some people on this call. You know, there's lots of interim assessment providers out there. You know, US is a pretty assessment heavy place. Something that's kind of unique to NWEA is how much time we spend on these linking studies, which is important for you all because it actually provides an indicator of proficiency from a test that is not the proficiency assessment. So it's, you know, it's easy to go to Texas, get star scores, and you have kind of a direct measure of student proficiency. But then there are limitations to that. It's only in the spring. It's only in grades 3-8, you know, things like that. True for pretty much all states. So, but then the challenge of going to an interim assessment provider, whether it's an iReady or Cambium or Map Growth, is okay, well, then you have it more often, you have it in more grades, but there's not really an indicator of grade level proficiency. And we try to kind of thread that needle by the linking studies that Sue mentioned. And you can find every one of those online. I think there are 38 of them active for 42 states right now. And so that's where we go and get state summative assessment from all of these states. We then compare it to MAP growth scores, do something called equipercentile linking, and we're able to come up with both fall, winter, and spring, basically projected proficiency indicators for all the students. So if you were doing a study, oh, and this is true in science, by the way, not in every state, but you could think of going to Texas and saying, Sue might correct me, I forget if they test in 4th or 5th grade, and then 8th grade. But you could say, all right, you know, it's great. We want to look at growth as an outcome measure, but we also want to look at proficiency. And so MAP growth doesn't really work for us there. It kind of does because we have those proficiency cut scores. So it really is a way to try to have it both ways. You can actually get a measure of if a student is on track for grade level proficiency with like a fall data point.
Thank you. Any questions about those details?
Megan had a question in the chat. Does that limit on instructional efficacy research apply to data received by a vendor via instructional connections?
I think you're asking, Megan, if you have connections to a district administrator, and that district uses NWEA, and that district chooses to share with you their NWEA data, then it's perfectly acceptable to use NWEA data in a curriculum efficacy study. It's just that we at NWEA can't share it directly with you, bypassing the districts. Does that answer your question, Megan?
She's
Yeah.
part of what she might be getting. Oh, I'm sorry. Go ahead, Megan.
Sorry, I was multitasking, eating lunch while on this call. Sorry. No, I was just specifically asking about that instructional connections program, and you know the district opting in to us receiving that data specifically via the instructional connections program. If that's that limit about, you know, then applying that to instructional efficacy research applies, or is that kind of a very separate legal contract kind of a question?
The short answer is I'm not really sure. I think it would probably depend on the instructional connections because it's not just like an us versus them kind of thing where it's like, oh, if it's an HMH product, it's fine. If it's not an HMH product, then we don't talk about it. Because obviously the instructional connections are something in the middle. You know, think of something like IXL being a good example. And so if someone were to come and say, I want to study, you know, something using data provided through an instructional connection, or I want to actually study the efficacy of an instructional connection using map growth data, we've never had anyone do that before, so I don't think we have a lot of precedent for it, but it would certainly be something we could explore. Oh.
One caveat, you might notice if you scroll through that list of instructional connections for science, it's very sparse, if any, so it's still kind of in the infancy of us finding good instructional connections for science, just since the implementation of NGSS high quality curriculum has intentionally been a lot more slow than the implementation of, you know, Common Core curriculum and resources. So there's currently probably not a lot of science instructional resources, but that's still a valid question for the other subject areas too.
And the last thing I'll say about this is, you know, everything Sue said was absolutely true and really important context. This doesn't come up that often. We will occasionally have third-party companies that, like, say, McGraw-Hill, I'm just picking someone, you know, has hired the RAND Corporation to do an efficacy study for them, and RAND then comes to us fast for data. That's kind of a classic example of where we wouldn't, you know, just provide data for that purpose. I don't think that's most of the people on this call, you know, are involved in this. You know, those are more, I would imagine you all are more basic science policy researchers who are interested in does certain types of instruction benefit students. And so I don't think this is going to apply as much for folks like you all. But again, I'm probably the least expert in terms of science ed policy research on this call. So.
Okay. You ready to finish this up? Got a few more slides here. And slides. What I'd like to do now is actually share, go into some detail about some of our COVID research, and then just give you a brief overview of some bright spots work that we did, just to give you a flavor of the kinds of research that can be done with our NWEA science data. So like I said, one example of the kind of research that NWEA does support is examining system-level trends, such as how COVID-19 disruptions affected science achievement. And in our analysis, we did not follow individual cohorts of students, but we did examine schools that consistently administered NWEA science assessment across the study period from 2019 through 2024, I believe, so that we could compare really school level performance by grade before, during, and after the pandemic. And using that RIT scale as a common metric, this school level approach lets us estimate average changes in science achievement while minimizing bias from inconsistent testing schedules. And here I'll share some of the actual findings from that COVID work. And I want to walk you through what this table is going to, what this graph is going to show you. 2019 is our baseline year. That's the spring of 2019 was before COVID achievement, before COVID impacted achievement. So it shows months to catch up to those 2019 achievement levels on the vertical axis. And then grade is on the horizontal axis, really ranging from grades 3 through 8. And 0 represents our baseline achievement levels in 2019. So anything above 0 means that there are additional months of instruction needed to catch up to 2019. So the higher the bar above 0, the worse things get, with more months needed to catch up. On the other hand, anything below 0 is actually a good thing on this graph, and it would mean that the average achievement of students in that grade and year was higher than the average of 2019. They don't have any months at all to catch up. They don't need to catch up at all. And so we also have values for spring in 2 calendar years after 2019. So teal will be the spring of 2021. That's kind of right in the middle of the disruptions caused by COVID-19. And then the yellow shows spring of 2024, which is the spring when we're looking at, hopefully, recovery time. So both relative to spring 2019 as the baseline achievement. So in 2021, we see that grades 4, 5, 6, and 8 were hit the hardest, with students between 2 and 2.5 months behind in those grades, while students in 3 and 7 were about 1 month behind their 2019 peers by the spring of 2021. So not too surprising. By 2024, we actually had some excellent news for elementary science. Students had caught up to or even exceeded their 2019 peers by 2024 in grades 3 through 5. So in fact, the average achievement of 4th graders in 2024 was higher than that of their peers in 2019, and that's why you see that negative value in the months to catch up metric. But the picture is bleaker in middle school. 6th graders made some progress by 2024, but 7th and 8th graders were actually further behind in 2024 than they were in 2021. So in the period that we had hoped would be recovery for science, we see that 7th and 8th graders, who happened to have been actually in 4th and 5th grade during the pandemic, were doing worse than they were than even their 2021 peers. In fact, 8th graders were more than 3 months behind their 2019 peers by the spring of 2024. So this is another example of the kind of research that NWEA supports. And this is our work identifying bright spot schools, so schools that demonstrate unusually strong growth in reading or science, and that also serve students that are traditionally underserved by schools. So this slide shows the relationship between school context on the horizontal axis and minimum growth in either reading or science on the vertical axis. So we put their growth in the average school growth in reading and the average school growth in science together as a pair. We pick the minimum value, and that's what's graphed. So whatever their growth was in one subject, it was at least, that's the lower of the two. They achieved at least that much in science, in reading and science, if that makes sense. So the context index really combines the percentage of students who are Hispanic or Black with the percentage eligible for free or reduced price lunch. So this is really an indicator of what percentage of students really fall into that category of students who are traditionally underserved by schools. That horizontal dashed line marks the top 5% of schools in terms of growth. The vertical line marks schools with higher context index values. So then in that upper right quadrant, you can see schools that meet both criteria. They were both high growing and serving higher needs student populations. And these highlighted in red are our bright spots. So this analysis really showcases how map growth data can help identify promising schools, not to infer causality or evaluate specific programs, but to surface places where exceptional growth is occurring so that educators and policymakers can learn from them. It's a really good illustration of how system-level research with NWEA data can inform equity-focused conversations and highlight areas of success within challenging contexts. So now you might be wondering, how can I get NWEA data? Well, we have an intake form, and I'm going to copy that so I can paste it in the chat. And I'll also share my email with you. But basically, you complete this intake form, you share your research plan with us, we estimate the cost to pull the data, you sign a data agreement, and then we send you the data over a secure file transfer protocol. I want to emphasize that when we estimate the cost to pull the data, we're not selling the data. What we're doing is charging for the time it takes for us to pull the data, and including the time to actually do the legal agreements that we have to have in place to be able to share data based on all of our agreements with districts. So I'm going to share that link with you in the chat. But that's really the end of our formal presentation, and I want to really stop here and see what questions you have.
It might help to give a little example. This wasn't for specific to science, but to give an example just of what this looks like. And we do this quite a bit in, math and reading, but we're trying to get more people to do science research and try to help our data further science education, hence this conversation. So we've had folks come to us a number of times with a list of schools. Maybe it's 5 schools, maybe it's several thousand schools with the NCSIDs, and they have determined that those schools are unique in some way, whether it's schools that use a particular curriculum, design their middle school science classes in some way, or even that they're micro schools. And they are interested in data for those schools as well as data on comparison schools. And so they come to us and say, we want test scores on these students. We'd also love some CCD covariates, school percent free and reduced lunch, urbanicity, school percent Black, things like that. Maybe they want to know regional codes, so which states are in the Pacific Northwest and things like that. And so we find out how many we have, because strangely, not everyone is a map growth partner. Plenty of people are working on that, but we find out what kind of coverage we have for those treatment schools, identify how many students over time. We can do longitudinal cohort designs, cross-sectional designs, and then we'll create a comparison group. So 500, 5,000 randomly selected schools over the same period of time. We kind of get a base estimate for how much time it will take to pull those data, and then create a scope of work, and that then goes through the details that Sue just mentioned. It really very much works at like a district or school level kind of policy level. The data are student level, but because we're not able to give you things like identifiers. So if you wanted to say, well, I know Bobby got 6 hours of this treatment and Katie got 3 hours of this treatment, you're not going to be able to do external merging for privacy reasons. So that's where really at like the school or district level is where I think this pays dividends. If you were really interested in student level identifiers, that's where kind of going direct to the schools can work best, because we don't have permission to give out PII. So like even if we really loved your study, we just can't do it. So just the 2-minute version of kind of how this flow kind of goes. And because we don't, as Sue said, we only charge for the time, the time for someone like Sue or me to pull and prepare the data set, it's relatively inexpensive. Because it's really just the FTE necessary for the legal agreements and to run the code. So the simpler the pull, the cheaper it is. If there's lots of complicated data manipulation we have to do, it ends up becoming a little more expensive. But I see there's some questions coming in, so let me stop talking.
There was a question about whether the recording of the session will be shared, and the answer is yes. NARS it automatically was recorded as we started, and NARS will be sharing that recording, I believe, on their website, and I will make sure that if you email me, I'll make sure you get it. I will figure that out for you.
Question about item level data. People are usually much less interested in item level responses than they are student level, school level data. In the 3 years I've been here, I've never seen an external data request for item level data. There's no inherent reason that would be, not open to a conversation. The limitation would just be, you can imagine NWEA probably doesn't want someone doing a diff analysis and then writing a bunch of papers about how map growth is terrible. So I think it would depend a lot on the use case. And that would be specified in the contract, just what is allowed to be done with this data. So there are probably instances where certain types of items, there's a broader policy question about, do types of items seem to work better for girls or, for low-income students or something like that. I think there's probably possibilities out there. It's just a little bit of undiscovered country. Those are also really big data files. Imagine a couple million students, now multiply it by 40 items per test event with several test events. It can get pretty nuts. Sorry.
Yeah, I think dissertation ideas are a great space for NWEA data if you're a policy ed researcher, because why go to the trouble of developing your own assessments and collecting all that data when you don't have the time and money to do it? Instead, spend a little bit of money and get some excellent data that you can answer all sorts of interesting questions for. So yeah, thank you, Jaima. If I'm not pronouncing your name correctly, I apologize. But I think that's a really great use case.
And we have had, NWEA used to have something called summer research interns. It's been a couple of years now, but we used to have every summer almost, we would have a research intern that was doing psychometric work with item level data, almost as like a, practice data set, just playing around and running different like IRT models or something like that on data. So I'm sure there's a way we could do something. It would just depend on the nature of it. And we do have several people that are doing dissertations with map growth data now. That have reached out to us and gone through this exact same process, just never related to science. Got to get more people using science data.
Any other questions? We thought this might take an hour and a half. We scheduled it for 2 hours, and we're not even hit an hour yet. But that is the full presentation, and I really appreciate everyone, joining with us today. And I hope this was informative, and I hope it sparks some ideas for you on how you might actually leverage this really valuable national resource that we have available to us, especially given the current policy context and how difficult it is to get funding to develop and use your own assessments. So thank you all so much for your time, and I hope you all have a wonderful, wonderful day. Thank you, Susan. Thank you, Scott.